Hello everyone, my name is Farhan Umarnadi Pulukadang. My ID number is 131182009, and in this video I'm going to show you uh, about creep phenomena for heat resisting alloy. This video is made as an assignment for the course of Structure and Properties of Material MS 2240. So what is creep? Creep is the deformation of solid material under persistent mechanical stress. In general, it occurs at the very least 40% of the melting point of that material. It is temperature dependent. It is also time dependent and occur in stages. So below here we have two examples of strain versus time graph. So each of the colorful curve, red, yellow, and green, it represents exactly the same metal, exactly the same material, with exactly the same dimension. However, it underwent different circumstances. The ones on the right, it underwent exactly the same stress, but different temperature, and the ones on the left undergoes the same temperature but different level of stress. And as you can see, the ones that undergoes the highest temperature and the high stress takes the least time to rupture. However, they have a differing initial strain point. This is another visualization of the creep test. So each line, each color represents the temperature, and this temperature remains constant throughout the creep test. And each line they have points, and each points they have x and y coordinates. So basically the y represents the stress and the x represent the rupture time, and that's and the what is meant by rupture time is the time needed from the very beginning when the experiment is just start to be conducted until it really ruptures. And this is done in a represented in a logarithmic scale. That's why if you actually see the scales here, some are tightly packed and some are sparse. As mentioned before, creep occurs in stages. The primary stage, high initial strain rate, decreases over time as work hardening takes place. So the epsilon zero, the initial strain, as you can see, it's from this point, from when the strain is still zero until epsilon zero, the strain rate is really high, almost approaching infinity, and then it gradually decreases because of work hardening. So when a material undergoes plastic deformation, it experiences an increase in strength and hardening, and because of that, the strain is hindered by that, and thus creep is hindered and the creep rate decrease. Next is the secondary stage, in which a balance between recovery and work hardening, minimal strain rate. The majority of creep process takes place in this phase. And so when the creep phenomenon takes place, the vast majority of the time will be in here in the secondary stage. So the strain rate remains constant. If you would derive this, say d epsilon over dt, then you will have a constant. And so uh, the spread of the strain remains constant. It remains rather minimal. However, since the secondary uh, really did, really does take a long time, and after a long time, it finally done enough damage for it to overcome the strength of the metal and reach the territory stage, and the strain rate will increase significantly, and finally the metal will rupture. So here are the equations of creep with respect to the stress and temperature. So when you plug in all of this value, you will come up with a constant, and that's why it's called steady state. And it's actually also the case in here, because when you're doing the temperature, you keep the temperature constant, and that's why also the stress will be constant too, and that's why the strain rate will also remain constant. And thus at the given constant temperature we have this equation. So how does a creep occurs? There are several mechanisms of creep. First is diffusion, which is divided into two: bulk diffusion, which is Nabarro-Herring creep, and grain boundary diffusion, or Koebel creep. And the other one is dislocation creep, which is also divided into two: climb and glide. So a little bit of review on diffusion creep. Uniaxial stress in the crystal cause potential difference. So this is the crystal within the metal, and then when uniaxial stress occurs, this will one side, one parallel side actually, so there will be two sides, upper and lower, will experience tension, and as a compensation, the perpendicular side will experience compression. So the vacancy will move from here to here. So from the higher potential to the lower potential. But how do the vacancies move? Well, that's a matter of whether it is Nabarro-Herring or Koebel creep. So Koebel creep is a type of diffusion. It occurs at lower stress and elevated temperature, but not as high as Nabarro-Herring. Mass transport occurs along the grain boundary. So when there's a stress here in the crystal, the vacancy will move from here to here. So it will only move along the grain boundary. Nabarro-Herring creep is the other type of diffusion creep. It occurs at almost the same level as Koebel creep, almost the same stress level, I mean. However, it occurs at a higher temperature than Koebel creep. And this is the important part: mass transport occurs through the grain boundary. So what does it mean by through the grain boundary? Is that when there is a tension here in this side, in this direction, so this is the two parallel side, so the perpendicular the pair of perpendicular side will experience compression, and the movement of the vacancy will actually be through it. So like this, it if we visualize it, it kind of formed like a curve. So it kind of like went into the interior of the crystal. So it kind of like forms a curve. Dislocation creep and power law. So as mentioned, there are two types: glide and climb. In glide dislocation creep, so if it's visualized, it will somewhat be like this pretty much. So The dislocation may originate from anywhere in the crystal, and then it propagates, it moves, um, well, not necessarily propagates because it doesn't increase in quantity, but it moves until it reaches another grain boundary, and then it stops. However, uh, in order to overcome that, the dislocation can actually go through even further, and that is when climb uh, takes place, because the dislocation actually climb above the glide plane, and that's why the dislocation can spread even further. And so to describe the strain rate with respect to those two phenomena, we have this equation, the general power law equation. So this is the strain rate, and then this is a creep mechanism constant. So each creep mechanism have its own constant, and this is the stress. Uh, this one you can read it here, but this is the important part. M 3 to 5 climb controlled creep, and 5 to 7 glide controlled creep. So the strain rate with glide will actually be faster. In my personal opinion, why glide will be faster? Because when the creep is climbed, it will actually takes more effort for the dislocation to spread, because it has to climb, uh, it has to overcome the obstacle for the dislocation to spread, and that's why the strain rate will be lower. Larsen-Miller parameter. So Larsen-Miller parameter is a data extrapolation method. Uh, it allows script test data to be extrapolated at lower temperature and longer time regime. So this is the equation. It takes temperature and stress rupture time as the variable. The Larsen-Miller parameter really makes it easier to conduct script tests. So say if regarding the stress or the temperature that is exerted on the metal specimen will actually cause the metal to fracture only after a very long time, so we can actually change the variable so that the metal specimen will fracture at a much quicker time, and then from the data that we have obtained we can come up with the Larsen-Miller parameter, and then we can extrapolate the data so that we will obtain the data with respect to exactly the same material with the same dimension, and we can know the actual rupture time, as if the metal had been ex had been under had experienced a significantly lower stress or temperature in creep phenomena. In order to overcome creep, we would need the light alloy for that. In general, the higher the melting temperature, the higher the elastic modulus, the bigger the grain size, and the better resistance against creep. Why is that? Because smaller grain size allows more grain boundary to slip. And the usage of alloy for that can resist creep is very extensive in the industry, such as jet engine and steam turbine, etc. The alloy that is used in this task, of course, it has to be able to withstand creep, and in order to do that, oftentimes the resistance to creep rate is improved by solid solution alloying and precipitate phase formation. That's it. That's all from me. Thank you.